Okay, we're going to start with number 1 in your Hardy-Weinberg problem set. And this is the same one we worked in class, but that was the first time you had seen it. So if you need to see it again in order to prepare for your exam, I wanted to go through it one more time. And so in this problem, we've got students taking a test, and on the test, you're either going to pass or you're going to fail. And so we've got 96 who are going to pass, and we've got 4 who fail. And whenever we do these problems, we have 2 variables. It's our P, and we have our Q. And you remember that P is the variable that we use for the dominant allele, and Q is the variable that we use for the recessive allele. And since we've only got 2 alleles, and it's given as a frequency or a percentage, we have our 2 variables. The first is that P and Q together have to equal 1, or 100%. And then we have the second equation, which for right now we're not going to talk about. We're just going to kind of put up here. But it's the one that's kind of scary, but it's the one we're going to use our P and our Q variables. And so with the information we're given at the beginning, we've got these 2 different phenotypes. And remember, the phenotypes are what you see, but your phenotype could come about from multiple genotypes. And so just to make this easy on us, let's go ahead and use A. Okay? So for our problem here, we're going to say A is the dominant allele, and A is going to equal pass. Whereas little a is going to be our recessive allele, and that's going to mean fail. And so that means that these 96 that have the A, the ones who passed, they have either big A, or they're heterozygous big A, little a. Either one of those genotypes is still going to give you a passing or dominant phenotype. Whereas with the ones who failed, they can only be one genotype. They have to be little a, little a. And that's because the only way you can get the recessive phenotype is if there's an absence of dominant alleles. There's only one genotype which would do that, which is little a, little a. And so whenever you get started on these problems, I told you guys in class how the dominant members are not going to be very much help because you don't know which genotype they are. I could write this equation if I've got big A, and I got big A, little a. Big A is P squared, and big A, little a is 2PQ. So I could say that P squared plus 2PQ equals 0.96, 96%, or 0.96, that's the frequency. But I can't do anything with that formula. We've got 2 unknown variables. There's nowhere else for me to go. But instead, if I talk about the ones who failed, which is 0.04, they can only be one thing. They can only be Q squared. So that means that Q squared is going to equal the 0.04. And again, that's why you always have to start with the recessive phenotype. If you try to do anything with the dominant, you're going to get stuck. So you've got to do recessive first. So Q squared, let's make that look like a square. If Q squared equals 0.04, remember that is my homozygous recessive genotype, or little a, we're all talking about the same thing, it's the recessive phenotype. I want to get Q. Remember, Q and Q squared are not the same thing. Q squared is little a, Q is just how many little a alleles exist at all. So to get Q all by itself, I have to get the square root of Q squared, which is Q, and then the square root of 0.04, which is 0.2. So if Q is 0.2, now, right away, I should be able to find P. Because you can put Q into this equation, but you're still going to have a big mess. You don't really know what to do about P. Or just use this one, P plus Q equals 1. So if Q is 0.2, I can substitute 0.2 in for Q. And I get P, which is 0.8. So these two numbers, and accidentally marked out my P, but P equals 0.8 and Q equals 0.2. Once you have those, you're pretty much done with the problem for any of these. You start with your recessive genotype. You then work to find your frequency of P and Q. Just those alleles all by themselves. Once you have them, now you're just going to go and plug it in to your P squared plus 2PQ plus Q squared to calculate all those other genotypes. And so at that point, it's a lot easier. But the part where most of you guys are going to make a mistake is number 1, Q squared and Q are not the same thing. Make sure you get that straight in your head. They're not the same thing. Don't make that mistake. The next is you need to understand what you're being asked. If you're being asked for heterozygous individuals, heterozygous individuals are 2PQ. If you're being asked for homozygous recessive individuals, that's Q squared. If you're being asked for the frequency of the alleles, or the frequency of the dominant and recessive alleles, you're being asked for just P and Q all by themselves. And then finally, if you're being asked for like homozygous dominant individuals, that would be P squared. And so the hard part isn't really the math, it's knowing what all these variables mean. So as you're studying for this, what I would really do is sit there, go down, and think about all the different variable combinations you can make. And it's 5. There's 5 different things you can make. It's P squared, 2PQ, Q squared, P and Q. And for each one of those, ask yourself, say it out loud, practice, describing what this is. What is P squared? How is that different from P? If you know what Q is, how is Q different from 2PQ or Q squared? Like what does that mean? What do those different variables stand for? And if you can do that, go back and look at your problems, you'll probably have a much easier time. But the hard part is not the math, don't get confused with that. It's knowing what all these different variables stand for. And so that's where most people mess up. Make sure you fix those in your study.